My name is Sergey Levin, and I'm going to talk about offline reinforcement learning. A lot of what makes machine learning work, modern machine learning, the kind that has seen such success over the past decade, is the ability to utilize large data sets that enable broad generalization with big high-capacity models that can make use of them. This can allow us to do things like recognize objects and images, translate text, recognize speech, and so forth. By and large, the commercial applications of machine learning that have been the most successful are basically applications of supervised learning, recognition, perception, and so forth. But let's step back a little bit and ask an even more basic question. Why do we need machine learning? And to start towards an answer, we'll ask an even more basic question. Why do we need brains? To answer that, we'll ask somebody who actually knows quite a bit about brains, Daniel Walpert, who's a very well-known neuroscientist studying motor control, knows quite a bit about brains, and he has this to say. We have a brain for one reason and one reason only. That is to produce adaptable and complex movements. Movement is the only way we have of affecting the world around us. I believe that to understand movement is to understand the whole brain. So what I would provide is a kind of a postulate inspired by this, that maybe we need machine learning for one reason and one reason only, and that's to produce adaptable and complex decisions. Now, of course, for a machine learning system, decisions don't just mean movements, they could be virtual decisions. In some cases, these are obviously apparent. For example, a robot deciding how to move its body, that's a decision. An autonomous car deciding how to steer the steering wheel. But some decisions are less obvious. For instance, you could say, well, when you recognize an object in an image, you produce a label. Is that really a decision? Well, usually not. The decision is not the label. The decision has to do with what happens afterwards. For example, if you tag a user in a photo, you're really making a decision about how to interact with that user, or maybe how to interact with their friends. If you have a camera trap that's meant to detect animals in the wilderness, you're making a decision that will affect downstream conclusions that you draw about where those animals are present. So any kind of output of a machine learning system is in fact a decision, and it leads to a consequence. So if we can have machine learning systems that reason about these, they should perform better. Machine learning, in a sense, is automated decision making. Supervised systems provide a number of assumptions that make this automated decision making seem a bit easier, such as the fact that data points are independent, or that your output doesn't influence future inputs, or that you have provided ground truth labels at training time. More general decision making problems don't have these assumptions. If you're steering a car, controlling a robotic arm, or doing a number of other decision making tasks, current actions do in fact influence future observations. Your goal is to maximize some utility or reward, and typically you don't assume that your supervision contains optimal labels. But these simplifying assumptions in supervised learning are in some sense an illusion. These are not just issues for control. In many cases, real-world deployment of ML systems that look like supervised systems have feedback issues that violate those convenient supervised learning assumptions. For example, if you have a system that predicts how traffic will behave, and then users use this system to decide where to drive, their behavior will actually change the traffic. If your system doesn't account for it, then it will not make optimal decisions about which route to recommend to users. If ultimately ML is always about making a decision, why don't we treat every machine learning problem like a reinforcement learning problem? Reinforcement learning is the branch of machine learning that deals with decision making, so shouldn't we all be using reinforcement learning for all of these settings? Well, here's the problem. Reinforcement learning is really two different things. First, it's a framework for learning-based decision-making. It replaces the conventional supervised way of thinking, where you map an input to a label based on ground truth supervision, with a more decision-focused way of thinking, where you map inputs to actions, and those actions then influence future inputs. Grounding your problem in a sequential decision setting can make it more applicable to the real world, and that's actually very desirable. The second thing that reinforcement learning provides is an active online learning setting for control. And this is the classic diagram from the Richard Sutton textbook, where you have an agent, it interacts with the world, collects a little bit of experience, improves, and interacts some more. It's a loop where you interact, use that little bit of interaction to update your policy or model, and then repeat the interaction and do this many, many times. It's fundamentally an active and online setting. The first aspect of reinforcement learning is very important because almost all real-world learning problems look like this. Almost all real-world learning problems require you to make decisions, and those decisions have consequences. If the decisions did not have consequences, there would be no point in having a system do this. However, almost all real-world learning problems also make it very difficult to have a system that is active on online. Imagine you are training an image recognition system, and every time you train it, you have to do online learning. That means you have to collect an ImageNet-sized dataset every time you retrain your system. That would never be practical. But you might say, well, reinforcement learning kind of works, doesn't it? It works for games, it works for robots, it works for beating the world champion at Go. But there's a really big gulf between the kinds of settings where reinforcement learning works and the kinds of settings where supervised machine learning systems have attained the best results. And it's a gulf of generality. The supervised systems generalize to diverse open-world settings, like any image on the internet or any utterance spoken by any person. To get that kind of generalization with an online active learning framework where you throw out your data each time you update your model, you would need to collect ImageNet-sized datasets for every training run, and maybe even for every iteration. So that would never be practical. So could we somehow make RL look more like supervised learning? Can we retain the benefit of handling feedback, reasoning about decision-making and consequences, and maximizing utilities, but still make it convenient to train our systems from datasets like we're used to in supervised learning? So we have these two views, the online view and the decision-making view. The online view is fundamentally closely related to on-policy reinforcement learning. But we can do RL without on-policy learning. What we can do is offline reinforcement learning. This is when you have a dataset that is provided to you, a dataset that may have been collected by people, baseline policies, hand-designed controllers, and so on, and you're going to use that dataset to distill out the best policy you can just from the data without any additional data collection. And then you will deploy that policy. In contrast to supervised learning, this does not involve copying what was done in the data. You're not trying to do exactly what the data did, you're trying to do it better by using data as evidence of how the world works. But in contrast to classical online reinforcement learning, you're not trying to collect more data each time you improve your policy. So the offline RL workflow essentially looks like this. Collect a dataset using any policy or mixture of policies. This could be humans performing the task, it could be some existing system, it could be random behaviors, or any combination of the above. And this is only done once. Then run offline RL on this dataset to learn a policy. You could think of this as the best policy you can squeeze out of the data. Then deploy this policy to the real world, and if you're not happy with how well it does, modify the algorithm and go back to step 2, reusing the same data that you did before. So we don't collect new data to redo step 2, we reuse the same data but we modify our algorithm. If we can get such methods to work, we can apply RL to settings that don't ordinarily look like RL problems. For instance, inventory management, where you dynamically decide to adjust inventory levels based on features that you observe about your users and customers. You could use historical data that you've collected about how inventory levels, purchases, and other decisions affected your revenue in the past, and then use that data to optimize a new policy for the future. Planning medical treatment and diagnosis plans. Decide how to optimally treat a patient, or at least what recommendations to make to a physician, based on histories of past treatments. Scheduling scientific experiments, controlling robotic systems, and many others. In today's talk, I'm going to discuss why offline RL is a difficult problem, why it requires new algorithms, how we can design some offline RL methods, how we can evaluate those methods to determine if they work or not, and how do we then apply them in reality, and why is that good? But let's start with the problems. First, a quick primer to value-based reinforcement learning. In reinforcement learning, you have an agent that selects an action A, and the world responds with states S and rewards R. The agent's goal is to construct a policy, which is a distribution over actions conditioned on states, in order to maximize the RL objective, which is the cumulative expected sum of rewards. A very useful object for doing this is what's called the Q function. The Q function is the expected sum of rewards you will get from now until the end of time if you start in state S, then take action A, and then follow your policy pi. If you can learn the Q function for a particular policy, you can improve that policy by taking an action with probability 1 if it is the argmax of the Q function. This is guaranteed to be at least as good as your previous policy and usually better. You can also skip the middleman and directly learn what is called the optimal Q function by minimizing the difference between the left-hand side and right-hand side of this Bellman equation. Essentially, if you can make your Q function at every state and action equal to the current reward plus the maximum over the next time step Q value, then you will recover the Q value whose corresponding argmax policy is the optimal policy. And this leads us to a very natural choice of algorithm where you collect data consisting of transitions. A transition is S, A, and then S prime. And then you minimize the difference between the left-hand side and right-hand side of this equation for every transition, for example, by minimizing mean squared error. Oftentimes we'll use the letter y to denote the target value, the right-hand side of this equation. Now in this talk I'm going to focus entirely on approximate dynamic programming methods, that is, methods based on Q functions. There are other methods for RL as well, but I'm disregarding them in this talk. So a basic sketch of an off-policy algorithm using this idea is based on the principle that you don't need on-policy data to make the left-hand side equal to the right-hand side. So you can collect the data set using some policy and store it in a buffer. And we're going the basic building block of this data set, just like x comma y is the building block in supervised learning, here the building block is S, A, S prime R. Right? So this is called a transition, a state, an action, a next state, and the reward obtained from that transition. In an inner loop, we'll sample mini batches from this buffer. We'll minimize the squared difference between the left-hand side and right-hand side of the Bellman equation, and then we'll repeat this some number of times. Occasionally we can go out and collect more data. You can think of it graphically like this. You've collected some transitions into your data set. You're going to run this process of minimizing the difference between the left-hand side and right-hand side on that buffer, and occasionally you can go and get more data, but if you're doing offline learning, you would skip this step. I would, as an aside, mention here that a more typical use case is to do offline learning first and then do some online fine-tuning, and we'll talk about that later as well. But for now, we'll talk about just the offline setting. So we instantiated this principle about 3 years back at Google in a system called Qt-opt. So Qt-opt was basically an offline learning system with online fine-tuning whose aim was to test the hypothesis that large-scale offline plus online training could actually enable generalization in the real world, kind of at the same level as what we saw from ImageNet. So we collected a huge data set, in this case of robotic grasping data. We had this highly distributed system, and then we tested it in a variety of very complex robotic grasping scenarios. So first of all, the system worked very well. It was able to pick up a wide range of objects, test objects that it had never seen before, difficult objects, small objects, large objects, transparent objects, flexible objects. It could even react to perturbations from adversarial humans. For a monocular grasping system from RGB images, to my knowledge, this is basically the best system out there. It gets a success rate of 96% on very difficult unseen test objects. But for the purpose of this talk, the interesting question is how the purely offline version of this compares to a version with online fine-tuning. So the offline data set consisted of 580,000 transitions, and there was an additional 28,000 collected for online fine-tuning. So the additional fine-tuning data is negligible in terms of its size. The success rate of the offline method was 87%, and it rose to 96% after fine-tuning. But if we look at this as a failure rate, the failure rate is 3 times larger, more than 3 times larger, from the fully offline version. So something is going on here. It's not just about the amount of data. Something about that online interaction somehow makes it work. Or, put another way, the purely offline training is not good enough. Why? Well, part of the intuition here is that offline RL requires a kind of a counterfactual query. Imagine that you have training data for driving an autonomous vehicle. And the data comes from humans, and the humans were good drivers, so they always stayed kind of in the middle of the road where they were supposed to be, or at least in the middle of their lane. And now the policy needs to figure out what is the optimal action to take in this situation. Should it go straight, or should it veer off to the left? Now, of course, we all know that going straight is better in this situation, but what the policy is really what the RL algorithm is really trying to ask is, if I took this different action than I had taken in the data, would it be better or worse? The issue here is we can't really know this if we haven't seen this action in the data. Online RL algorithms don't have to deal with this problem because they simply try this action and see what happens. They learn by trial and error. Offline RL has to figure out whether the data set is sufficient for us to draw a conclusion about an action that was not taken or insufficient. They somehow have to account for these unseen actions, ideally in a safe way, ideally without assuming that an action that was never taken is a good one. But at the same time, they have to make use of generalization to come up with behaviors that are better than the best thing in the data. So sometimes you want to take an action that was not taken in the data if it is similar to other actions that were taken and where you can confidently infer its likely value. But you don't want to take actions if you have no way to determine their value. So how does this problem show up in practice? Well, about a year after that Qt-opt work, several of my students wanted to investigate this question. They collected an offline data set for a standard benchmark task, the half cheetah, and they found that offline training immediately results in a drop in performance. And on the surface, this looked a lot like overfitting. We thought, well, maybe it's overfitting, so we should add more data. The blue here shows 1,000 data points, the red 1 million, and there is no difference. Adding more data does not fix the problem. Everything gets a reward of minus 250. Now remember that a Q function is an estimate of expected reward. So we can ask the Q function how well it thinks it will do, because it's trying to predict the total reward it will receive. These are the Q function's predictions. The y-axis here is a log scale. So the red curve with 1 million data points thinks it'll get 10 to the 7th power, and instead it gets minus 250. Whoa, that is weird. We're seeing this massive overestimation. Why is that? Well, to try to understand this, we first need to understand distributional shift. When we minimize the error, the squared error to some target values, we're really doing empirical risk minimization. We're minimizing our empirical risk under some training distribution P of x. When we do this, we can ask a question. Given some test point x star, is f of x star going to be correct? That might seem like the most basic question, but it's actually surprisingly subtle. We know that the expected value of the error under our training distribution P of x is going to be low. But the expected error under some other distribution P bar of x in general will not be low if P bar of x is not equal to P of x. Even worse, if we draw a data point x star from P of x, even then we can't guarantee that its error is low because we're only minimizing the error in expectation. So it'll be low on average, but it will not necessarily be low on any individual test point. Now we might say usually we don't worry about this because we're doing deep learning and we know that neural nets generalize so well that we don't worry about distributional shift. Well, sometimes that's actually true, but what if we do something even worse? What if we pick our point x star by directly maximizing f of x? Well, now we're going to get in trouble. Imagine the green curve is our true function and the blue curve is our fit. The fit is very good in most places, but if we pick the point x where the blue curve is largest, we'll pick exactly that point with the largest error. Put another way, if you maximize with respect to the input to a neural network, you're essentially asking for an adversarial example. You're asking for an input that will fool the network into producing a large output. And you can always find such an input. Now, where does this happen in QLearning? Well, let's rewrite the Bellman equation in a slightly different way. Instead of writing it as a max, I'll write it where the next time step is in expectation under pi nu, where pi nu is that distribution that gives a probability 1 to the argmax. This is exactly the same equation. I've just written it in a way that makes it a little more apparent that what we care about is the expected value of our Q function under the distribution induced by the new policy pi nu. Now, we have these target values, and our training objective is to regress onto those target values, expected risk minimization, under the distribution pi beta. So on the last slide we had P of x, now we have pi beta. Pi beta is the unknown policy that collected the training data. We don't know what pi beta is, but we know that some such distribution exists, and that's what produced our data set. So we know from the previous slide that our expected error will be low under pi beta. We expect good accuracy, therefore, when pi beta is equal to pi nu, because we're evaluating under pi nu, but we're training under pi beta. But wait a minute, how often is that going to be the case? Pi nu is our new policy. The whole point is to improve over pi beta. So in general, pi nu will not be equal to pi beta, and even worse, pi nu is explicitly selected to maximize our Q values. So just like the picture on the previous slide, we're essentially asking our policy to produce adversarial examples that fool our Q function into outputting the largest values. And that's why we see this massive overestimation on those benchmark tasks. Okay, so now that we know the problem, how do we design offline RL algorithms? One classic approach explored in a number of prior methods is to modify the training for pi nu so that it doesn't just blindly maximize the Q function, but also respects some constraint where it doesn't deviate too far from pi beta. The rationale is that if pi is close to pi beta, then distribution shift is limited and our error should be low. So this solves distributional shift, right? That means no more erroneous values. Well, this is a fairly old method. It's an idea that's been explored in a wide range of previous works and has also been used in a number of more recent papers. But it has a number of issues that make it difficult to build truly effective offline RL methods with this principle alone. The first issue is that we usually don't know what the behavior policy pi beta is. The data may have come from humans, from hand-engineered controllers, from scripted policies, or even have been collected randomly. And in general, it could be a mix of all of those things. A second and more pernicious issue is that this is both too pessimistic and not pessimistic enough. It's too pessimistic in the sense that, imagine your behavior policy is totally random. Then this constraint is essentially saying, don't be too deterministic, remain somewhat random, or else you'll incur distributional shift. But that makes no sense. We want to find the best policy supported under our data. We don't necessarily need to stay close to a random or ineffective behavior policy. As long as we're inside of the data, we should be fine. At the same time, this can be not pessimistic enough, because you could deviate by relatively small amounts from pi beta and still pick out adversarial examples. Remember what I said before. Even if the test point is sampled from the training distribution, your error is not guaranteed to be low because your error is only low in expectation. So even a small KL divergence will not necessarily guarantee that you do not suffer from distributional shift. We found two principles for addressing this issue that do seem to work well and do seem to present a solid foundation for offline RL methods. Option one is to avoid ever evaluating actions that are not in the dataset. Not just actions within the training distribution, avoid any action that is not in the training set itself. So if these black points represent your training set, your curve will usually be very good on the black points themselves. So as long as you stick to just the training points, you don't care that your function extrapolates in crazy ways. The second principle is to train the Q function so that out-of-distribution actions never have high values. So this means explicitly finding those erroneous peaks and pushing them down. Now, you don't know their true value, so you can't push them to their true value, but what you can do is you can at least lower their value so that they are never the max. Basically, so that the maximum actions are always the ones that are in distribution. And I'll discuss some algorithms in both categories. First, I'll talk about option one, and I'll start with an algorithm called Advantage-Weighted Actor Critic, or AWAKE, which was primarily developed by Ashwin Nair. The idea here is going to be the following. Imagine a basic actor critic algorithm, where you update your Q function with pi nu, and then you update pi nu to be the argmax of the current Q function. Now, doing this naively would yield this argmax policy, and in general, this maximization is going to query the Q function at actions that are not in the dataset, because as you're maximizing this, you're actually changing pi, sampling from pi, and testing the Q value of that action. Can you train the actor without querying out of distribution actions? So here's an idea. What if we train the actor with weighted regression? Essentially, we do weighted max likelihood on the dataset. So we have our dataset, which is sampled from pi beta, and we're just going to maximize the log probability of all the actions in the dataset. Well, okay, so that's no good, right? Because that's not actually using the Q function in any way. It's not actually trying to make good actions more likely than bad actions. It's trying to make all the actions likely. But what if we then weight this objective? We'll introduce a weight W, and we'll choose this weight so that actions with higher Q values have a higher weight. So now pi nu is only allowed to increase the probability of actions in the data set. It's never going to go and increase values of actions that are not in the data, except through generalization. But the weights will ensure that the good actions have their probabilities increased more than the bad actions. Intuitively, this makes sense. Theoretically, if we choose our weights to be proportional to the exponentiated Q values with some temperature lambda, we can actually prove that the resulting policy pi nu, in the limit, solves a constrained optimization problem. It's maximizing the expected Q value subject to a constraint that it doesn't deviate too much from the behavior policy pi beta. The intuition for why this is true is that your actions always come from pi beta, which means that regardless of the choice of weights, you'll never deviate too much from pi beta, especially if you choose your temperature correctly. So the punchline here is just by optimizing our actor with a weighted max likelihood objective, we can actually enforce this constraint approximately and get a policy improvement step that never has to test out of distribution actions. Now, by itself, this is not a sufficient principle for a fully offline reinforcement learning method. It works okay, but it's not great. What it's really good for, though, is offline RL with online fine-tuning. So here's a little animation. We get some demonstrations with a success rate of 24%. We do offline pre-training on those, and then we do online fine-tuning. And this ends up working a lot better than alternative techniques for offline pre-training. Here are some learning curves. The red is this proposed method. The other curves are other offline RL methods or other standard RL methods. And you can see that Awake here, the red curve, performs significantly better during online fine-tuning, even though after offline pre-training, it's not necessarily always the best performing method. But if we want to develop a good fully offline RL algorithm, what we can do is we can also take care of the issue of auto-distribution actions in the queue update itself. So before we got rid of auto-distribution actions in the actor update, now let's get rid of them in the critic update. So the trouble, of course, is that we still need to evaluate the expected value of our queue function under pi_new. And remember, just having a constraint is not enough to fully rule out those adversarial examples, those bad situations. So here's how we could think about it. This expected value of Q with respect to actions, let's call it V of S prime. V is just another neural network. And we can train V in various ways. One way to train it is to train it with regression onto Q. So we'll sum over all of the states in our data set and we'll minimize the difference between V and Q. So we could use the mean squared error loss for our loss function. Now that's no good, right? Because that's not using the policy pi in any way. So in the same way that that original naive max likelihood loss didn't use Q values, this one is not using pi. This will just give us the value of the behavior policy. Because the action here comes from pi beta, not from pi_new. If we were to plug in the action from pi_new, then we would get the value for our new policy, but that would require querying an action that's not in the dataset. If we only use the actions in the dataset, we get the value of pi beta. But here's an interesting observation. In our dataset, we might never visit the same state twice, but we are likely to visit multiple similar states. So as long as the value function, v of s here, generalizes a little bit, in reality, we have a distribution of different values at each state. Remember, we don't literally see the same state twice, but we see very similar states multiple times, where we take different actions in those similar states. And therefore, we get a distribution of possible values that we might get, a distribution of possible QSA values, because we have multiple nearby states, each one with a different action. Now, this distribution is induced only by the actions. We're just talking about the Qs. We're not talking about the actual rewards you see in the future. If you use the mean squared error loss to regress V onto Q, then you get the expected value of this distribution. So you'll get something in the middle. And that's the value of pi beta. But you could take the value kind of out on the tail. You could take the highest value that still has a non-trivial probability. That's the value of the best policy supported by the data. And that will actually lead to policy improvement. So could another choice of loss function give us that? Here's an idea. This is called expectile regression. The idea is that we're going to take our mean squared error loss and we'll modify it so that the negative branch has a smaller weight than the positive branch. So we'll pick tau to be some large value like 0.9, and our symmetric mean squared error loss will turn into an asymmetric loss that penalizes positive errors less than negative errors. This can be shown to actually give you that upper expectile. An expectile is like a quantile only for squared losses. Formally, you can actually prove that if you choose tau appropriately, then the value function will not regress onto the expected value of Q, but actually to the max of Q, where the max has taken over actions within the set of actions for which their probability under pi beta is larger than epsilon. If you use the loss with tau for a big enough tau. So that's pretty cool. We just showed that we can do regression using only the actions in the dataset. We never have to query any action that was not in the dataset, but we just change our loss function and we get the effect of a max. So this leads to an algorithm that we call implicit QLearning because it performs implicit policy improvement. So the two steps of implicit QLearning are train your Q function with a Bellman backup, only use a separate function approximator for V, and then train V by regression onto Q using the dataset states and actions, but with this expectile loss. And this algorithm was developed primarily by Ilya Kostrikov. So the scheme here can be shown to maximize the Q values with respect to all actions that have a non-trivial probability under the behavior policy. And you can think of the resulting induced backup as having an implicit policy that is also greedy. It also takes an action with probability 1, but it only takes the one that's the argmax within the support of the data. Now that's the theory, but in practice, of course, the method never actually queries the Q function at any action that was not in the dataset. And that's very important because that avoids any chance of exploitation. So now we can do value function updates without ever risking auto-distribution actions. And when we're done, we can extract the policy using the same weighted max likelihood procedure that we had in Awake. We'll see results for this procedure soon, but let's first talk about option 2. So option 2 is to train the Q function to avoid out-of-distribution errors altogether. remember that our issue is that we get this overestimation due to the maximization procedure, because when we pick the max, we'll pick exactly that peak where the Q function makes the largest error in the positive direction. So what we'll do instead is we'll modify our QLearning objective so that it has the regular Bellman error minimization term and an additional adversarial optimizer that minimizes the Q value of those actions that are chosen by an adversarial distribution mu, which itself is trying to maximize the Q values. So mu is trying to find these actions for which the value is very large, and the regularizer pushes them down. We can actually prove that this procedure, which somewhat resembles adversarial training, learns Q functions that are lower bounds on the true Q function for pi if you use a large enough alpha. This leads to an algorithm called conservative QLearning, which was developed primarily by Aviral Kumar. The actual conservative QLearning algorithm uses a slightly more refined bound. In addition to this first term that minimizes the Q value for actions chosen by mu, we also have a second term that pushes up on the Q values in the data. Now, this might at first seem very strange because we're trying to combat overestimation and we're actually maximizing Q values in the data. But let's think through what this procedure will actually do. If all of the high Q values are for actions that are in the data set, then the first term will push them down and the second term will push them up. And these two terms will actually balance out. So they will, on average, have no effect. But if the high Q values are for actions that are outside of the data set, then the first term will push them down and the second term will instead push up on something within the data set. And that means that the policy will shift towards the data set and the terms will balance out again. Now, once we use this procedure, we're no longer guaranteed to have a lower bound for all states and actions, but it turns out that we are still guaranteed to have a lower bound over all states in expectation over the actions under our policy, which is what we really want. Now, before I tell you how CQL performs and how CQL compares to IQL, let me discuss a little bit how we should be evaluating offline RL methods. So the first question is, what do we expect offline RL methods to actually do? There's some bad intuition. One piece of bad intuition is that we expect it to basically do imitation learning. I don't think this is a very good intuition. Imagine the following scenario. You have a start point in green, an end point in orange, and you have these demonstrations D. Imitation learning, we just try to match the demonstrations. We don't really need offline RL for that, although we can actually show that offline RL is provably better than imitation learning, even with optimal data under some structural assumptions about MDP. So for some MDPs, offline RL will actually do better than imitation learning even in this setting, but that's not really its primary purpose. A better intuition is that it's trying to get order from chaos. So imagine that our data looks more like this. Now clearly if we just imitate that data, we are not going to get anything remotely reasonable. But offline RL can put together the best parts of each trajectory and recover good behavior. One thing that you could imagine doing is this kind of stitching. If you have a path from A to B and another path from B to C, you should be able to recover a path from A to C. But this is simply the simplest and clearest example. In reality, you might get a kind of a micro-level stitching. Imagine you have data from many different human drivers that are all suboptimal in various ways, but they each do some part of the problem well. An offline RL method should be able to extract the very best parts of each of them to get a kind of superhuman policy. A policy that does as well as the best possible human in every situation, even though there's no one human who does that well everywhere. So offline RL is actually extremely powerful. It can take highly suboptimal data and figure out a way to solve the problem, or it can take kind of medium reasonable data and extract a superhuman behavior, in principle. But in order to understand whether our algorithms actually do this, we have to test them in the right way. So if we have algorithms that can properly perform dynamic programming, we can take this idea much further and get near optimal policies from highly suboptimal data. Here's a really vivid example of this. Let's say that you want a robot to grasp an object from an open drawer. Okay, you can train for this task, but if the drawer is closed at test time, then the robot won't know what to do. But now imagine that you have some previous data. You have previous data of other skills: closing drawers, opening drawers, closing other drawers, and repositioning objects. None of this prior data has the skill you want. None of it has grasping the object from the open drawer, and not all of it is relevant. But if you include all of the data in offline training, then you can actually figure out how to put together the right pieces for whatever new problem you might encounter. So, for example, if the drawer starts out closed, a policy trained with offline RL on all this data would be able to figure out that it should open it and then pick it up because it can do temporal composition. It can figure out that it can stitch together those parts of skills that it saw before. If the top drawer is open and the bottom drawer is closed, then it can close the top drawer, as you'll see in a second there. You can close the top drawer, open the bottom one, and then pick up the object. If the drawer is blocked by some object, it can pick it up, lift it out of the way, then open the drawer, and then pick it up. Now, these demonstrations that you're seeing were all produced with CQL using just a very particular data set that has these varied skills, and the second, third, and fourth video you're seeing on the bottom includes a composition of those skills that was never seen together in the data. We created a data set called D4RL to evaluate offline RL methods. It includes standard Mujoko gym locomotion tasks. It includes maze navigation tasks that are specifically intended to test temporal compositionality. So here the goal is to travel from the lower left to the top right, but none of the training data actually includes that entire trajectory for the large mazes. It only includes transitions between other pairs of start and end states. Tasks where you get human data for dexterous manipulation, tasks for manipulating objects in a kitchen, and applications like traffic control and image-based driving. The gym locomotion tasks are intended as simple diagnostics, and they don't test for compositionality. The maze navigation tasks are kind of the real tasks. They evaluate compositionality, and the other tasks are applications. Unfortunately, a lot of offline RL papers don't really test on anything except for the gym locomotion tasks, and those are actually the tasks that don't test compositionality, so arguably they're not really testing improvement over behavioral cloning. Okay, so as promised, here are the results for various methods. The first three rows represent essentially methods that are variants of behavioral cloning. Regular behavior cloning, percentile behavior cloning, and decision transformers. They're all basically trying to copy the data. These methods represent new offline RL methods proposed in 2021, which I didn't get a chance to discuss, but I encourage you to look them up. This is Awake, which performs fairly poorly in purely offline mode because it's really designed for fine-tuning, and the last two columns are CQL and IQL. One of the things to notice is that on the gym locomotion tasks, most good methods perform similarly to a good behavioral cloning implementation. So CQL and IQL perform better, but really these are tasks that don't really require a heck of a lot of complex offline RL because they don't really require temporal compositionality. But if we look at the and maze tasks, we see a significant improvement for methods that properly handle compositionality. So here you can see that both CQL and IQL have a threefold improvement over the performance of behavioral cloning and about a 2x improvement over the next best previous offline RL method. In fact, some of these are actually subsequent to CQL. So I guess what I would say here is be careful when evaluating offline RL methods. Offline RL can do things that imitation learning simply can't, but we need to test the right things to measure that. So we need to use data sets that actually evaluate whether your method is doing something that requires offline RL. Here's also a comparison for fine-tuning. So in each entry I have a number and then an arrow and then another number. So the number on the left of the arrow is what you get after offline pre-training. The number on the right of the arrow is what you get after online fine-tuning. And you can see Awake actually fine-tunes pretty well, but sometimes it does very poorly, especially on the ant mazes, not because it's not fine-tuning, but because it's failing to initialize well in the offline phase. CQL performs great in the offline phase, but it's too conservative for fine-tuning, so always pushing down those Q values basically hampers exploration. IQL generally performs the best for fine-tuning because it has both a good offline initialization and good fine-tuning performance. So we discussed these two options: avoid ever taking out-of-distribution actions, or train the Q function so that those actions are not a problem. IQL implements option 1, and CQL implements option 2, although there's a little bit of reverse chronology here because CQL was actually proposed about a year prior to IQL. Now, how do these methods compare? Well, CQL has fewer hyperparameters, and we also have much more sophisticated workflows for tuning those hyperparameters offline, so in some sense it might actually be easier to use. It has better theoretical guarantees. We actually have a pretty good understanding of why it works and what to expect from it. IQL appears to perform slightly better, and it's much better in fine-tuning mode. Overall, though, what I would say is that we still don't know which principles are going to be the most effective in the long run, so it makes sense to explore multiple different options, and if you're interested in doing research on offline RL, there are many open problems for you to tackle. But before I conclude, let me say a few words about applications. The power of offline RL can best be illustrated by how it changes the reinforcement learning workflow. So if you want to use reinforcement learning in the real world, if you want to use standard online RL, here's what you would do. You would instrument the task so that you can run it, safety mechanisms, autonomous collection, etc. Then you would wait a long time for your RL run to complete. Then you would change the algorithm in some small way to improve it, and then you would repeat the entire training run, which could take hours or even days. And once you're happy with all this, you would throw out everything and start over for the next task that you want to learn. The offline RL process looks a little different. You collect an initial data set using a variety of data sources. Then you train a policy with offline RL, and then, just like before, you would change your algorithm in some small way, except when you change it, you don't have to recollect your data. You just have to retrain the policy on the data that you already have. And if you want more data, you can collect more data and add it to an ever-growing data set and then retrain the policy. So you don't collect all the data from scratch, you collect just a little bit more data that you think you actually need. And when you're done with all this, you can further keep the data set around for the next project. Let me give you a few examples of where we've done this. So I mentioned this QTOP project where we did offline RL for robotic grasping. More recently, we've extended the system into a system called MTOpt, which learns 12 different tasks with thousands of objects and months of data collection. After we trained MTOpt, we had a new hypothesis. Could we learn these tasks without rewards using goal-conditioned RL? Okay, this is just a hypothesis we wanted to study. This talk is not about goal-conditioned RL, although I do think that was pretty interesting. But what I do want to emphasize here is the way that we resolved this hypothesis. We didn't go and collect a new data set. We simply took the data set we already had from MTOpt and trained a different policy, a policy that was conditioned on goal images, and trained to reach those goal images. Without a single additional episode of data collection, we could get this policy to work using a method that was a variant on CQL and actually get some pretty promising results. Here's a video of this policy in action. The lower right shows the goal image that is commanded to the robot, and the video shows what it actually does. There's no reward function here at all. The task is defined entirely in terms of matching the goal image, and it uses a conservative offline RL method based on CQL. One of the nice things about this method is, well, we could train it without any additional data collection, and once it's trained, it actually serves as a really nice unsupervised pre-training objective. You can kind of think of it almost like BERT for RL, BERT for robots. So you can train your goal-conditioned Q function with offline RL from all the data you have, and then fine-tune it with a task reward, and get pretty significant speed up and pretty significant improvements in generalization. So it's pretty neat that we were able to resolve this hypothesis without a single additional episode of data collection, and get this pretty cool offline unsupervised pre-training objective. Here's another example. In early 2020, my student Gregory Kahn collected 40 hours of robot navigation data for off-road driving. About 6 months later, Dhruv Shah, another student in the group, used this data to build a goal-conditioned navigational system that could be used for things like deliveries and waypoint patrolling. That worked very well. It could navigate over long distances without a single additional episode of data collection, entirely reusing those 40 hours that Greg had collected. And about 6 months after that, Dhruv Shah carried out another project, training a policy that could learn to search for objects in unfamiliar environments. Now, searching in unfamiliar environments requires enormous generalization, but again, he could just reuse the same 40 hours of data that already provided a large data set to bootstrap this research without any additional on-policy data collection, except of course for the actual searching step itself, which was a test time. Now, there are many other topics in offline RL that I didn't cover. One really big one is model-based offline RL, which is really a great fit for offline RL because it's offline. You can use plenty of compute and huge models for training your dynamics. So one work that I want to mention here is Combo. This is essentially a kind of a model-based version of CQL. So similar principles apply, conservatism, out-of-distribution actions, etc. But another thing you can do with offline model-based RL is utilize much larger models. So it's much more practical to use huge models like transformers, which is something we explored in a recent paper called Reinforcement Learning as One Big Sequence Modeling Problem. We introduced a system called Trajectory Transformer, which is basically a giant transformer model for learning dynamics. It captures some similar ideas to conservatism in that it models joint state action distributions and then keeps you within the high distribution actions. And the resulting model can make extremely accurate predictions. So what you're seeing here is not a simulation. This is actually a rollout from the model, making predictions using this transformer. We can also explore offline RL for multitask learning, and that's a very rich area of investigation. For example, we study how you can share data between tasks so as to minimize distributional shift. Remember, distributional shift depends on pi beta. When you choose which data from other tasks to share, you're actually changing pi beta, so you can do some really clever things there. And there are many more topics to explore in this area. But in terms of some takeaways, I do want to leave you with some discussion of open problems about the gap between the dream of offline RL and where we are today. One of the things that I think needs a lot more work is the offline RL workflow. In supervised learning, we have a very powerful workflow where we split into a training and test set, and we use something like a validation set to tune hyperparameters. What is the equivalent of that in offline RL? Can we tune offline RL methods without any online trials? We have a starting point in a recent paper that was accepted at Coral 2021, but a lot more work here is needed. Statistical guarantees. The biggest challenge is distributional shift. Can we make any guarantees about the performance of offline RL methods? There's plenty of initial work in this direction, especially theoretical work, but I think a lot more effort here is needed. And lastly, scalable methods and large-scale applications. I talked about some examples, but I think there is plenty of work for applications of offline RL outside of robotics, dialogue systems, data-driven navigation and driving, control of power grids, control of inventory management, logistics. So many more problems that could be tackled in the offline setting that are impractical to attack with active online methods. Well, thank you all for listening, and I would also like to thank and acknowledge the students that were involved in this research. Thank you.